Alrighty, so welcome to our 15th lesson in probability and statistics, and this one is called normal distribution. This might sound like binomial distribution, right? So the thing to remember, because it's easy to confuse the two, the thing to remember in binomial distribution is that you're going to have a fixed number of trials. Fixed number of trials, okay? The other thing that you need to remember is there is only two outcomes. Like, right? It's either green or not green, whatever it is, heads or not heads, okay? And then also the probability of success is going to be constant. So our P, the probability of success, is going to be constant. That is, it's always the same, okay? So like the probability of getting 6 on a die is 1 out of 6. Okay. All right. So it might be obvious in some cases, just dependent on what you're given. And in others, it might be a little bit more confusing. So that is binomial distribution. That's what we did our last lesson. Okay. So normal distribution, let's talk about what this means. So this is just a throwback, right? So mean, the symbol for mean is like the mu, right? It can also be x with the bar over it, and this just means it's the average, okay? All right. Standard deviation is the little OX, right? So that's how widespread the graph is. So let's just talk real quick about the graph that we have. So if we put our frequencies on our x-axis, okay, a normal distribution is going to look something like this bell curve kind of thing, like this, okay? And so it's always the case that right here, right down the middle, that is our mu. And then if I were to take this and see where like it changes direction, like right here, this distance right here to this distance here, this is our standard deviation, right? It's how spread out our data is, okay? Whereas if I had another graph, let's go like this, right? If I were to take this and have my graph look like this, okay? This might have a smaller standard deviation, right? It might be less of a spread, right? Or if I were to take it and look something like this, right? So it's like higher, but the spread would be smaller compared to the original one, okay? All right. So this is just going over some basics, and it's symmetric about the mean. So whatever happens on this side is also going to be happening on this side, okay? Symmetry means that if I take it, cut it in half, it looks the same on both sides. All right. So it's the most popular distribution in nature. So like the weight of people, the height of people, the amount of time spent in a supermarket, weight of a pack of coffee labeled 500 grams. These are some examples. Biggest things to kind of know about the area under the curve, right? So if they ask you like what is the probability or the area under the curve, they are finding a value. So the whole thing from the beginning of our curve to the end, the area under this whole thing right here is going to always add up to 1, okay? All right. So the probability of going from negative infinity, right, less than or equal to x, less than or equal to infinity, is going to equal 1 whole. That's 100%, okay? What if I told you that you have a curve, right? And this curve is a normal curve, which means that it's like looks like a little bit of a bell. And I told you that the mean is 15. So here's our mean, okay? And if I asked you to find the probability greater than 15, right? So we know that the whole thing, the area under the whole curve is 1 whole. So if I were to take this and cut this in half, if I just asked you for this part right here, that would make sense that it's half of it, right? So the probability greater than 15 is going to equal 0.5. Why did I not put the equal sign? Equals 0.5. That's half of it, okay? All right. So how this comes into play is whenever there's a curve, right? Our mean is the number that's like right down the middle, right? That's our normal curve. And the standard distribution is this is like 1 above this standard deviation above the mean, and this is a standard deviation below the mean. So if I were to take that distance, right, from our -1 to +1 right here, that percent is always going to be 68%. So this percent right here of the data is always going to be 68%. If I were to shade this completely, it would look like this, okay? So 60%, 68% of our data is going to fall between the mean, right, mu, plus or minus 1 times the standard deviation. Okay, so please write those notes down. If I were to go 2 standard deviations, right, so if I were to, here's our mean, if I go 2 standard deviations in either direction, that's going to be 95% of our data. So most of our data, 95% of it, is going to fall between the mean plus or minus 2 times the standard deviation. So the mean plus or minus 2 times the standard deviation, okay? And our final one to remember is between -3 and 3 standard deviations, right, of the mean. So mean plus or minus 3 times the standard deviation, 99.7% of our data falls there, okay? So those are 3 things that come in handy. Our calculator will give us the actual numbers, right? Especially if it doesn't hit any of those. So we're going to go through a couple of problems of that. So this right here is just a refresher, right? What we just talked about. So mean plus or minus 1 times the standard deviation is 68% of the data. So there's an actual problem here, right? So I'm going to show you in the example that we're going to be doing how to take this and plug this into our calculator. So let's go ahead and just do this problem right here. So how do we plug this into our calculator? Okay. So we're going to learn a new calculator button. Since this is a normal distribution, right? Looks like this, and it's not binomial, right? What we're going to do is we're going to hit second vars. And now we're going to be using normal CDF, option number 2. We will never use normal PDF in AISL, okay? So normal CDF. And look at the prompt, right? What is the lower? What is the upper? So it tells us for our problem that we're doing here, right? The mean weight is 75 kilograms. The standard deviation is 10 kilograms. So we want to find between 65 and 85 for our problem. So let's go ahead and do that, okay? So our lower is 65, gave it to us, right? The upper is 85, gave that to us as well. The mean is 75, that was given in the problem, and the standard deviation is 10, okay? So if I were to take this and just hit enter, enter, right, I get 0.682, which is about 68%, okay? So that should make sense. So now if I go, right, here's my mean is 75, right? And then between 65 and 85, we just found out that the area, the probability of being in this set right here is 68.3%, okay? All right, pretty straightforward. Now what if I go 2 standard deviations, okay? So if I go somewhere over here, okay? So between 55 and 95, right? 10 below, 10 above, okay? So now we're going to go ahead and use that, right? So I'm going to hit second vars again, normal CDF, right? Always option 2. So now I'm changing my lower to 55 and I'm changing my upper to 95. And leaving the mean and the standard deviation the same, I'm just going to hit enter and it gives us 95%, okay? So these are where these numbers come in handy. And so you can do the third standard deviation, right? 3 standard deviations below and above of 45 and 105, that's 99.7, okay? So this is just a refresher. The whole curve is 1 or 100%. Half of it is going to be 50% of that. So again, you can go through and read this part right here. And this just goes over how to use probability, the normal normal CDF in the calculator, right? So we're always going to use normal CDF, never normal PDF. And it just tells you what to put in, right? Your min, your max, your mean, your standard deviation. Those are the things that you need, okay? So let's do it. Let's try a problem. So the birth weights of newborn babies are normally distributed with a mean of 3.39 kilograms. So if I'm drawing this, right, this is the whole curve, right? The whole thing altogether is 100%. Good. So they tell us that the mean, let's change the color here, the mean, which is straight down the middle, right, is 3.39. That is our mu, okay? And it says, and a standard deviation that is unknown. So we don't know how wide our curves are, okay? So it does tell us that 28.39% of babies have a weight between 3.19 and 3.59. So let's answer the first one first, okay? So part A, what is the probability that a baby weighs more than 3.39 kilograms, okay? So what do we want, right? We want 3.39 greater, okay? So if we know that the whole thing is going to be 1, right? This whole thing right here is going to be 100%. Then half of that, right, just this is going to be 0.5 or 50%, okay? That should be pretty intuitive at this point right now, right? Whole curve is 100%, half of that is 0.5, okay? Hopefully pretty straightforward. All right, next. What is the probability that a baby weighs more than 3.59? So let me just go back and erase this right here. Let's get back our curve. So we have something that looks like this. Okay, so somewhere on this right side is where 3.59 is, okay? And somewhere on this left side is where 3.19 is, right? So this is 0.2 away and this is 0.2 away, okay? So they're the same distance away from the mean, okay? All right, so we definitely know that. So they're telling us that 28.39% have a weight between 3.19 and 3.59. So this whole distance right here to right here, this is going to be 28.39%, right? Which is 0.2839. All right. So let's see if we can figure this out, right? So we want to know the probability that a baby weighs more than 3.59, right? We want this part right here. So what do we know so far, right? We know that the whole thing, like from here, all of this, including the part that we want, is 50. That's half, right? So we could say that 0.5, 0.5, which is a half, minus, so just the whole thing, this whole thing right here, right? All of this is where that 28.39% comes. So this side is half of it. So let's see what that is, right? If I take my calculator, 0.2839 divided by 2. All right, so I get that number right there. So minus 0.14195, so 0.14195. And this will give me the probability that a baby weighs more than 3.59, okay? And I have to do this because I don't have the standard deviation. So 0.5 minus 0.14195. I could have just gone up and grabbed the answer, but it's all good. So I have 0.358, right? So this is 0.358. Where's my 5? There we go, okay? So that is the probability. If I wanted to estimate it, I could have used that normal CDF. So just watch real quick. Second vars, always option number 2. So my minimum number is going to be 3.59 because that's where we're starting from. There is no max, so I'm just going to put 9, a whole bunch of 9s. And my mean is 3.39 because it gave it to us, right? And our standard deviation we don't know, so we could estimate 0.55, okay? So about a little bit more than half, and we do get the same answer, okay? But then again, this is an estimate, and we're doing that because the standard deviation is unknown. If we're given the standard deviation, we could figure this out easier, okay? So now, last note is if we're asked how many, like how many babies weigh more than 3.59, so what we would have to do here is take the answer that we got, right? So 0.358, and then this is how many of our babies. So we would need to know like a total number of babies here. So I'm gonna go ahead and just say there's 100 babies altogether. So if I said how many babies weigh more than, right? So we have to do 0.358 times 100. So I can take my calculator here and do that pretty simply, right? Times 100. And that gives us 35, almost 36 babies, right? So this is 35.8 babies. 35.8 babies. Weigh more than 3.59 kilograms. Okay. All right. So these are just a couple of examples going through. I'm going to ask you if you can to try the problems that are here. So numbers 1 through, what is it, 3? Yep, 1 through 3. So go ahead and do those and then check your answers with me. That rhymes. Okay. Take care.